Yo. All right, here we go. We're going to go over question 3 from the 2018 AP Calculus AB exam. Let's just get right after it. All right, it says the graph of the function g, the derivative of f. So as soon as I see that, I'm like, all right, they gave me g, and it turns out that g is the derivative of some function f, right? So that's pretty important. Take note of that right away. So the function g is piecewise linear. So from -5 to 3, we just have line segments. You can kind of see those right here. But after that, g is going to be equal to this parabola from 3 to 6. So if you see from 3 to 6, we have this nice little parabola right here. Okay, so it's kind of they're mixing it up where they give you a part of an algebraic expression for the function, then also this graph where we're probably going to have to rely on the fact that we know these are line segments. All right, so good little question. All right, so here we go. So it says if f of 1 equals 3, so that's some initial condition for f. I know the 0.13 is on f. It says what's the value of f of -5? Okay, so that's what I want to find. So there's a couple ways to do this. I've been showing you both recently. I'm going to go with the way that I particularly like, which is, hey, if you want f of -5, then it probably would be a good idea to get f of x. And the question is, can you express f of x fairly easily? And the answer is yes, you can. Right? If you have a derivative, which we do, we have f prime. It's this graph, but we'll just say we have f prime. And you have a condition for the function f, then it's going to be really easy for you to express f as an integral function, right? So obviously I'm going to have to make an integral symbol. And now to make this a function of x, I'm going to put an x right there. Now, what would I have to integrate in order to get f? Well, the answer would be f prime, right? You integrate f prime, you get f. So I could write f prime here if I want, or I can write what it's equal to, which is g, which is what I'm going to write. So g. Now, I guess I technically could write g of x dx here, but I'm going to write g of w dw because this variable is a dummy variable. Why is that? This is a definite integral. So at the end of the day, x is getting dumped into here. So that's why this is what makes this a function of x. You could put any variable you want here. All right, a lot of times people put t, right, when we're talking about f of x. My t's look like plus signs, so I'm using w. All right, so then what's next? Well, the next part of this is, all right, so this now is a function whose derivative is f prime, but then you have to take care of this part, which is f of 1 equals 3. And you can do that pretty easily, right? We've done this a bazillion times by just kind of filling in where I put these boxes here, right? If I put a 1 there and a 3 there, that's going to do it. This now is a function whose derivative is f prime, right? So that gets satisfied. And also where f of 1 equals 3, that gets satisfied, right? If I wanted to, I can write the plus 3 over here as well. All right, now this isn't part of the problem, but I'm going to show it anyway. All right. So if I wanted to check this, like how do you, wait, what? This is a what? This is a function whose derivative is f prime. So let's check it. So let me do f prime of x. So f prime of x would be the derivative. I'm just going to bust out the command notation here. The derivative of this expression, right? So you're like, okay, not too bad. You should know, hopefully, that the derivative of a sum is the sum of the derivatives. So the derivative of 3 is 0, and then it'd be plus the derivative of this integral, which I'm going to, for note flavor, take my time and just write derivative of the integral. So now how do I take the derivative of an integral? Well, that's the fundamental theorem of calculus, right? Basically, these undo each other after the fact that a variable swap takes place. And this constant down here, whether it's 1, 5, or a bazillion, is going to be negligible. So you're just going to end up getting g of x, right? So think about it. If you were to find a function whose derivative was g, then you chuck x in, minus, then chuck in 1, then take the derivative of that. Well, now that first part of that, you're going in a complete circle with just the new variable x. So you're going to go back to g, but with g of x. The second part of that is just going to be a constant. The derivative of that is going to be 0. And that's why this doesn't matter. I know, I know I outlouded that, and that might not have made sense to you. But you should know the fundamental theorem of calculus by now. All right, so that's the first part of the check. So yeah, so I definitely found a function f whose derivative is g. So that's great, okay? So now what's the second part of this? The second part is, well, what about, call this like part A, part B here. What about this condition? Does the function I just found satisfy f of 1 equals 3? Well, in order to do f of 1, I put 1 in the function f where I see an x. Well, I see an x right there. So that's going to be 3 plus the integral from 1 to 1 of g of w dw. Just so we get the right ones here, f of 1, the 1 goes there, right? And so the integral from 1 to 1 is 0, so you just get 3 here. You get f of 1 equals 3. So that's satisfied. So again, this here took us 2 seconds to do, to come up with a function whose derivative was g, and that satisfied f of 1 equals 3. I just did this for really your notes or for refreshing. This is not part of the problem. You would not do this. All right, so then you're like, well, what do I do now? Well, now that you have f of x, let's go ahead and find f of negative 5. So then that would be 3 plus the integral from 1 to negative 5 of g of w dw. And the way you're going to do that now, I'm going the integral from 1 to negative 5, so I'm going that way, right? I'm going right to left. It's just going to be the net signed area, but everything's going to be a little bit bizarro because I'm going right to left. So like my delta x in that Riemann integral definition would be negative, and then my functional values are what they are, but it's going to swap the signs, if that makes any sense, okay? So I'll just say, hey, this is just net signed area. Net signed area. All right, so let's go ahead and do it. Let's make sure we don't make any mistakes. Duff, hook me up if I do. All right, so we'll kind of piecemeal this. So I have 3. That's part of the problem. And then plus now the integral, let's see, we'll go from 1 to 0. Well, that's a triangle right there. All right, so the area of that triangle is going to be 1/2 base. It looks like it's 1. Height is 2. I'm going from right to left, so negative delta x, positive functional value. That integral would be negative, so I'll put a little negative in front. Plus, this is just a flat line, so that's going to be nothing, so I'm not going to write that. Now I got this triangle right here, right? So the area of that triangle, and I guess I could do the whole big chunk as a trapezoid. I'm just going to choose not to. The area of this triangle is going to be 1/2 base, and then the height is, it looks like 1, 2, 3. And believe it or not, this integral would be positive because not only is my delta x negative, remember I'm going right to left, but my functional value is negative. So negative times a negative is a positive. So this integral is going to be positive. So I keep that positive. And then I'm going to add to that now this little rectangle here, which looks like it's a 1, 2, 3 by 1, 2, 3 rectangle, a 3 by 3. All right. And then I just kind of crunch these numbers here, guys. So we're going to get, let's see, here, those little 2's cancel. You're going to get 3. That's going to be plus a negative 1. That's going to be plus 3.5. This is going to be plus 9. 12 minus 1 is 11. 11 plus 3.5 is going to be 12.5. So my final answer is 12.5. And if I got a common denominator, I also could have expressed it, obviously, as 25/2. Okay? So the stuff in this left margin is basically the work that you would have done, not this. Stress that again. This is just for you coming up with this. All right? This is kind of how I like to do it personally. All right, let's move on to the next part of this question. All right, so it says the graph continues blah, blah, same thing, right? So I just recopied that. It says evaluate the integral from 1 to 6. Okay, so very kind of similar, maybe a little bit more straightforward, at least at first glance. So if I want to integrate from 1 to 6 of g of x dx, how am I going to do it? Well, that's going to be the net signed area from 1 to 6. So now why is this interesting? Well, because when you go from 1 to 3, that's no big deal because that's just net signed area. You can figure this out because it's piecewise linear. That's a geometric shape. But then when you go to integrate from 3 to 6, right, this is not a geometric shape that maybe we know the area formula to. So that's going to have to be done algebraically, right? Remember, this is a non-calculator question. I don't know why I'm coloring these in, but why not? Color it in. So the first step I would do is probably, break this up. So write this as the integral from 1 to 3 of g of x dx plus the integral from 3 to 6 of g of x dx. But remember, on the interval 3 to 6, g of x is this. So I'm actually going to put in what it's equal to, okay? And so now when I go to do this for this part here, it's the same concept. This is your net signed area. So we're integrating from left to right with a positive functional value. That means my integral will be positive. That's simply going to be, it looks like a 2 by 2 2 by 2 square there. All right, plus now this integral here. All right, so I'll rewrite this integral from 3 to 6 of, let's maybe pull the 2 out. 2 times x minus 4 squared dx. So the question is, all right, we could do 2 times 2, that's 4. How do we integrate this right here? So you could do a u sub if you wanted to, and you could let u equal x minus 4. Right, du would be dx, so it would work out real nice. You can change your limits since you're going to change your variable, and you can go through that whole process, and there would be absolutely nothing wrong with doing a u sub, other than the fact that maybe it's not the most efficient because it's going to take you time, and time on the AP test is huge. So you're like, well, if I did let u equal x minus 4, I would notice that the u would be linear. All right, and when we're doing linear u subs, there's usually, not usually, there is usually, they can be done in your head fairly easy. All right, you just kind of have to think of this as, all right, if I want to integrate stuff squared, right, the integral of that, just use the power rule here. It's going to be stuff cubed divided by 3. So in other words, 1/3 stuff cubed. That's just a power rule. But then you'd have to multiply by 1 over the derivative of stuff. Now, stuff is linear. It's 1x minus 4, and the derivative of that would just be 1. Now, if I didn't write this in, you'd think that you wouldn't have to do that, but you always have to multiply by 1 over the derivative of stuff. It's kind of like the reverse chain rule for integration, but as I've said a bazillion times, there is no such thing as the reverse chain rule, because this little procedure only works when your u is linear. All right, and then you can't forget now that I found this antiderivative, I have to evaluate this chunk from 3 to 6. All right, so now let's go get them. So I would have 4 plus, I would take this 2/3, pull it out, right? First chuck in 6, so 6 minus 4 cubed minus, then chuck in 3. 3 minus 4 cubed. That's f of b minus f of a. That's the fundamental theorem of calculus there. Right? I'm going to be a little bit lazy here. 6 minus 4. Actually, I hate doing that. That's 2. I won't do it. I won't be lazy. I'll rewrite it. Shame on me. Should not be lazy. Mathematical flow, right? It's all about mathematical flow, people. All right, so it's going to be 4 plus 2/3. 6 minus 4 is 2, so that's going to be 2 cubed. Minus 3 minus 4 is -1. That's going to be -1 cubed. All right, maybe we'll go this way. 4 plus 2/3. This is going to be 8, and then this is going to be minus 1. All right, so that's going to be 9. So you're going to get 18. All right, think about this. 18 over 3, that's 6. 6 plus 4 is 10. Your final answer there is going to be 10. All right, so solid little stuff there. You had to break the integral up first, realize that part of it can be done using net signed area. The other part could be done using basically a linear u substitution. Not that I would do it with a u substitution, because I wouldn't. But if you were to go after it, right, you'd let u equal x minus 4. Du would be dx, right? We do the whole deal where, hey, man, if we're going to change our variable to x, we should change if we're going to change our variable to u, we should change our limits to u. So when x equals 6, right, that would imply that u equals 6 minus 4, which is 2. And when x equals 3, u equals 3 minus 4, which is -1. Rewrite this now. I have that 2 out in front. Integral -1 to 2 of u squared du. And then I would integrate that. So I would get 1/3 u cubed. So I'd get 2/3 u cubed evaluated from -1 to 2. And if you think about it now, if you chuck in 2 minus then chuck in -1, all right, that is going to take you basically right here to this line right here. Chuck in 2, chuck in -1, the 2/3 is factored out in front. So that would give you that part of the problem right there. Okay, but again, doesn't have to be done because u is linear. And when they're linear, it's real easy to do them in your head. Okay? All right, so solid question. Let's go to the next part of this awesome question. Okay, so it says on this whole interval, -5 to 6, right? Open interval, really. All right, there's no or equal to. On what open intervals, if any, is the graph of f both increasing and concave up, and then give a reason for your answer. So to me, this is bread and butter stuff. If you want to know where f is increasing, then you should know that means when f prime is positive, right? A function's increasing when its derivative is positive. And if you want to know when f is concave up, well, then that means when f double prime is positive, right? The second derivative tells you about the curvature, the concavity of graph. The first derivative lets you know if it's increasing or decreasing. Now, remember, this graph of G here, they told you, is f prime. So you have it, you have the information for this right in front of your face. If this is the graph of f prime, this is basically a two-dimensional sine line. So whenever this graph is below the x-axis, right, f prime is negative. It's actually 0 here for a chunk of span right there. And whenever this graph is above the x-axis, then obviously, since this graph is f prime, this graph is positive, right? And it looks like we're 0 at this little instant here, okay? So this function f is going to be increasing from on the interval 0 to 6 because the derivative is always positive there. All right, so that takes care of that part. But now what about concavity? All right, how do I reveal curvature? Do I have any other cool colors here? Looks like I have orange. All right, we'll use concavity. We'll use orange. So that's f double prime. So if I'm looking at f prime, if this is the graph of f prime, I'll kind of put it in your face like that, then f double prime is the derivative of that. So that is represented by the slopes on this graph, right? So where would the slopes be positive? Well, that's whenever f prime is increasing. So the slopes are positive on that interval. The slopes are positive on that interval. And the slopes are positive on this interval. All right, I'm drawing in little tangent lines here. Okay, slopes are 0 over this interval, 0 over that interval, and 0 over that interval. So now if I want to figure out where the graph of f is both increasing and concave up, I have to see where the graph is above the x-axis with positive slopes. And if you look at that, that is happening from 0 to 1, because here we're above the x-axis and our slopes are positive, and then it's also happening from 4 to 6, okay? So we would say open interval 0 to 1, union with 4 to 6. I like using interval notation instead of inequality notation. And you basically say what I said here, you know, because, all right, f prime greater than 0 implies that f is increasing, and f double prime greater than 0 implies that f is concave up. Now, you might want to tell them how you got f double prime, you know, maybe make a note that f double prime represented by slopes on f prime. All right, I'd probably write that. A lot of the answer keys you'll see, they talk about that if f prime is increasing, then that means f is concave up, because that would mean that f double prime is greater than 0. So they'll say something like, instead of saying this, they'll say because f prime is increasing, right, then you have f is concave up. If f prime was decreasing, then f would be concave down. And so you could state that too. You should know that, obviously. I like talking about concavity in terms of the second derivative, specifically in terms of the sign of the second derivative. All right, so this is a bread and butter question here, boys and girls. Don't overthink this one bit. Basic concepts, all right here. Those are the basic concepts. All right, so let's rock and roll. We're almost done. Part D says find the x coordinate of each point of inflection. So for me, I see point of inflection, and I'm thinking change in sign of f double prime, okay? So it says give a reason for your answer. So the point of inflection on f, so change in sign on f double prime. So we just kind of talked about this, right? This in your face here was, this is the graph of f prime. So when is f double prime changing sign? All right, so maybe it's first prudent to find out when f double prime is 0. So f double prime is 0 over all of this, because all of these tangent lines would be 0. It's 0 here, it's 0 here, and it's 0 at that instant right there because that tangent line would be 0. Okay, I'm not drawing in all the tangent lines on these intervals, on these little constant parts of the graph. Okay, so that's where f double prime is 0. So 0 over 3 intervals and then 0 at a point. So now, where's the changing sign though? So like if we look at 4, immediately to the left of 4, if I drew in a slope, it would be negative. So f double prime negative over here. And immediately to the right of 4, if I drew in a slope, it would be positive. So f double prime is changing from negative to positive at 4. If you look at the other ones, I know nothing to the left here. Here it just goes from 0 to this would be positive. Here it goes from negative 0 over an interval, and then it's positive. So that means there's like a linear part of the graph there. So that's not a point of inflection. All right, so I guess they're trying to trick you here in that you got to know that it's going to change sign at a point, not over an interval. So this interval is not going to be a point of inflection. All right, and then here it's just going to be, I don't know why I changed the color there. It should have been blue since I'm making it positive, right? So here it's just going to be positive, then it's 0 again for a chunk of time, and then negative. So the only time it changes sign at a point is at 4. So you'd say that f has a point of inflection. I'm abbreviating, you don't, at x equals 4 because f double prime, which, by the way, what is f double prime in terms of how they labeled this, in terms of the graph of g, right? Well, wouldn't that be g prime, right? That makes sense, right? So if g equals f prime, then g prime equals f double prime. So because f double prime, which, oh, by the way, is g prime, changes sign from, what is it, negative to positive right here. And again, I guess to be similar in that you can say because f prime goes from, they do this sometimes, f prime goes from decreasing to increasing, not f prime, I'm sorry. F prime, duh. F prime goes from decreasing to increasing. So you can state it that way as well. I particularly like to state it in terms of the sign change. And then again, just make a note, even though you already did it, not going to have to do it again, that, f double prime, which equals g prime, represented by the slopes on f prime, which was g. Okay, so similar concept. All right, again, you think point of inflection, you think second derivative. All right, so change in sign of f double prime, or where f prime goes from increasing to decreasing. All right, I remember back in the day, I think it may have been Frank that said, so basically relative extrema on the graph of f prime go back and relate to points of inflection on the graph of f. And he was correct in saying that. All right, good stuff. Hope all is well. Be good. 2 weeks away, boys and girls, to test time. All right, so hopefully you're putting in the time and the work. Trust me, it'll pay off. Be good.